As a species trying to understand the boundless universe, the progress we made in the 19th and 20th centuries is absolutely unmatched in our hundreds of thousands of years of history.
Just 100 years ago, a blink for humanity, a mere instant for the cosmos, we still believed the Milky Way was the entire universe, a static, unchanging, possibly eternal and everlasting cosmos.
Newton's laws seem to support this idea perfectly. A clockwork universe, ticking along forever. All of that was about to change, dramatically, in just a few short years. Albert Einstein's general relativity would replace Newton's gravity, and with it, he would reveal the profound relationship between matter, energy, and the very fabric of space-time.
According to Einstein's equations, the universe could not be static. It had to be dynamic, always changing, always moving. And when we later discovered that the universe was indeed expanding, Einstein's bold prediction was confirmed. Einstein also predicted black holes, and those too were later proven to exist. Just another in his long list of predictions that turned out to be true.
But today, we're going to continue from right here, from black holes.
We've talked about them before. We mention them every chance we get. But today, we're going to look at black holes and the mystery they hold from an angle that might just shake some foundations.
Are you ready?
What makes a black hole a black hole? It's not the darkness. That's not what defines it. It's the event horizon. That is the defining feature of a black hole. This line we call the event horizon. One side is one reality. The other side is like an entirely different universe.
If you're on the outside, you still have a chance. If you can move fast enough, you can escape.
But if you're on the inside, forget every ending you've ever known. This is truly the end of everything for any object, a fate beyond death itself.
An ending that leads to the singularity. And within just a few seconds, you'd find yourself at the very center of the black hole, at the singularity itself.
The only thing left of you would be the extra mass you added to the black hole. As we discussed in our last video, black holes grow with everything they consume. They always gain mass. But wait! What does any of this have to do with the beginning of our universe? Incredibly strange, and we're about to find out. Now, everything in the universe. Let's try something together. Let's take absolutely everything and compress it down to the size of an atomic nucleus. And when we say everything, here's exactly what we mean. Here are our ingredients. Ordinary matter. The familiar stuff made of protons, neutrons, and electrons. Neutrinos, ghost particles that barely interact with normal matter at all. Dark matter, which has done everything possible to avoid detection, yet fills every corner of the universe. Photons, our beloved particles of light, carrying the energy of every electromagnetic event throughout all of cosmic history. And gravitational waves, ripples in the fabric of space-time, created every time a mass moves through the cosmos. Yes, these ingredients are all we need. When we look out into the universe, we can see roughly 46 billion light years in every direction. And when you mix all those ingredients together in the right proportions for the observable universe, you can use Einstein's legendary formula, E equals mc squared, to calculate the total mass of the universe. So here's our question. What would happen if we compressed everything
every last bit of it into a single point?
The answer is clear. The same thing that happens whenever you compress any large mass into a single point, a black hole.
And this is where things start to get really interesting.
And this is where the incredible power of Einstein's gravity enters the picture. If the mass and energy in question carries no electric charge, and if we assume it has no spin, then the size of the resulting black hole is determined by one thing and one thing only: the amount of mass. And as you may remember from our black hole video, we call this the Schwarzschild radius. In simple terms, it's the radius you need to compress any amount of matter into in order to turn it into a black hole. Once matter is compressed past that radius, the game is over. There is no other outcome. It becomes a black hole, period.
And if we took all the matter in the universe, compressed it into a single point to form a black hole, do you know what its Schwarzschild radius would be?
Almost exactly the size of the observable universe. Is that a coincidence? Could it be that we and everything around us came from a black hole?
Wait, we haven't even started yet. It gets even stranger.
In the mid-1960s, a discovery was made that would fundamentally change how we see the universe. When we looked into the void of space, no matter which direction we pointed, there was a remarkably uniform, low-energy radiation coming from everywhere. The temperature of this radiation was just a few degrees above absolute zero. It was an almost perfect black body radiation spectrum, as if it were coming from a hot thermal source. When first discovered, it was called the primeval fireball. Today, we know it as the cosmic microwave background radiation. In its simplest form, this told us that the universe was once far hotter and denser than it is now, and that it has been expanding and cooling ever since.
So if we rewind the tape, we can conclude that everything was once much smaller and far more dense.
And when we rewind all the way to the very beginning, we reach a singularity, the same type of singularity we only see in black holes. Points where density, temperature, and energy are so extreme that all known laws of physics break down completely. And when we look at the equations that describe a black hole, we encounter something truly extraordinary. For example, if you draw a line starting from just outside the event horizon to any point beyond, that distance can stretch from the Schwarzschild radius all the way to infinity. But on the other hand, if you draw a line from just inside the event horizon down to the center, to the singularity, you'll find that distance is the exact opposite. Zero. Infinity versus zero.
You might think, so what? What's the big deal?
But the mathematics is telling us something else entirely. When you swap the roles of distance and radius and compare the properties outside the event horizon with the properties inside, they are in every way exactly identical. Truly fascinating. Of course, our understanding of the universe has advanced dramatically in the last century. Two new discoveries shook the foundations even further.
The first was cosmic inflation.
The discovery that just before the Big Bang, the universe expanded at an incredibly, almost impossibly rapid rate.
As if some energy inherent to space itself from some kind of field drove this expansion, And only after the inflation ended did the actual Big Bang explosion occur. The second discovery was dark energy. As the universe expands, distant galaxies are accelerating away from us, moving faster and faster.
It's as if empty space itself has its own intrinsic energy, and this energy doesn't dilute as the universe expands. If anything, it seems to grow stronger.
And ever since these two discoveries, cosmic inflation and dark energy, scientists have been wondering if there might be a connection between them.
But what is that connection? Once again, it's black holes that may hold the answer.
Black holes gain mass with everything they consume, growing larger, and then, through Hawking radiation, they slowly lose mass again.
And this raises an avalanche of questions.
For instance, as the event horizon changes size, does the energy of space also change for an observer trapped inside?
Could the Big Bang, triggered by cosmic inflation, have emerged from a supermassive black hole?
Could dark energy itself be connected to black holes? And here's the craziest part. We know that new black holes are constantly forming throughout the universe. So does each one of them contain a baby universe inside? These are, of course, speculations, but they've been nagging at the minds of physicists for a very long time. Especially if your field of expertise is black holes, thermodynamics, entropy, general relativity, and the beginning or end of the universe. You simply can't avoid asking these questions. Many theoretical models have emerged to address these connections, but unfortunately, all of them have fallen short. They lack the essential qualities that a successful scientific model requires. First criterion, delivered with the weight of scientific standards, clear and definitive. No model has been able to reproduce the phenomena we've already observed and confirmed. None could propose a new claim that previous theories had failed to explain. Third and final criterion, completing the trinity of failure, definitive conclusion. And none could make testable predictions that differ from existing theories. The most ambitious of these models is Roger Penrose's Conformal cyclic cosmology, the idea that when one universe dies, it gives birth to a new one. Of course, we have no evidence for this, not yet at least. Just like all the other models exploring the connection between the birth of the universe and black holes. But all the possibilities we just discussed make it impossible to simply dismiss this connection. It's plausible that there is a connection between the birth of our universe and a supermassive black hole that may have existed before the Big Bang. And it's equally plausible that inside every black hole forming in our universe right now, there is a universe. But we simply don't have the strong evidence to prove it. Not yet. And that is the greatest challenge facing theoretical physicists, finding the faintest breadcrumbs of a new theory in the observable universe, finding the evidence that would distinguish this new theory from everything we already know. Without finding them, we can't speak of any reality. But ignoring this possibility entirely would be a grave mistake. So the question, what happens if you fall into a black hole, has a truly fascinating answer. If you fell into a black hole, you might provide the very raw material needed to create an entirely new universe. In an instant, you could become nothing, and then be reborn as an entire universe.
The Scottish comedian Craig Ferguson once wrote something in his book, Between the Bridge and the River, that captures this perfectly.
The universe is staggeringly large, incomprehensibly large, and there are two very important rules you need to know about the universe.
Rule number 1. Nothing lasts forever. Everything has an end. You, your family, your home, your car, the planets, the sun, everything.
Rule number 2, everything is infinite. Everything, it lives forever.
And as always, until we meet again, I'm glad you exist. Sending love.